In this demonstration, I would like to represent some of the shapes of Gaussian plumes to help you visualize how the Gaussian plumes look like as they emerge from a stack. We started with the diffusion equation, which is a parabolic partial differential equation, and its solution includes e raised to the power x squared. So the shape would be a symmetric normal distribution. In our problem, it was the diffusion in 2 dimensions, and with the velocity components, it can be simplified to dispersion coefficients in y and z direction. So we have to visualize a bivariate normal distribution. So at first, let's see the 1-dimensional normal distribution. Before that, there is a shape, and where the at a particular instant of time, if we see the concentration profile, so it looks like an ellipse of concentration, and on an ellipse with characteristic axis values, we have the fixed concentrations that can define an ellipse. So that will be visible in contour plot. The normal distribution is a symmetric bell-type distribution, and it has certain characteristics, well-defined characteristics of probabilities if we look from the same offset away from the mean value. In 2 dimensions, the Gaussian distribution, the bivariate normal distribution, uh, is proportional to e raised to the power minus x squared minus y squared. Of course, I have considered the standard deviation equal to 1 by 2, so that this has been converted into the standard expression. So we can see uh, a concentration profile like a symmetric cliff top. So this is for the concentration, and the stack emitting the the pollutants, it is directly below the axis of this top. So we can define a normal distribution in x direction and a normal distribution in y direction. And if we see the this one from the top, so we can define the cross section to be concentric circles, whereas the smallest circle, which is defined, if we cut that one like this, if we cut the shape in the horizontal plane, so the circle can be traced on the surface, and its value would be the highest. So similarly, the slices would give us the trace of a circle. In case the dispersion is not equal in x and y, in our case in horizontal and vertical directions, so the contour plot would not be uh, in the form of symmetrical circles. However, all these will be concentric. So at time t equal to 1, most of the particles will be at the stack height, and as the time progress, there would be dispersion, and ellipse can be defined in the plane. So this is the the plume facing view of the um, of this Gaussian distribution. And at t equal to t3, which is greater than T2 and T1. So we have been able to see rather more dispersion in uh, in the vertical plane. So this is the concentration shape. just to see that there are two normal distributions. So one can be traced like this. So this is in the y direction of the concentration, and one can also be traced in the vertical direction. So that is like a cross section like this. And this is not the symmetric one, since the dispersion in y direction and z direction are not equal. The contour plot would be represented in the form of concentric ellipses. Now, if we have the stack, of course, it is going to emit the pollutants at certain height. So we have to shift the vertical uh, component of the dispersion by h. So the plume profile in the vertical plane would be like this, that at the maximum concentration would be at the axis of the plume, and it will be propagating in the time and in x direction. Okay. Then there is going to be a problem when this profile is going to expand in with time in the x direction, in the downwind direction. So we will find that at this point, the plume is going to hit the ground, and all of this concentration will be predicted inside the earth. However, this is not going to be the practical case. This concentration is going to be settled on the ground. So therefore, we have to add all this concentration on the surface of the earth. So to figure out this calculation, this contribution of the plume, and add this one to this place on the earth, we use the method of images, which is to consider an imaginary stack. Here, I considered in arbitrary units of 3 scale height. So an imaginary stack is going to predict this concentration likewise above the ground. So we consider an imaginary stack at a depth minus h with the same mathematical procedure by shifting the z concentration axis to z plus h. And this will happen that this is the ground level, and we have the imaginary plume of the same height, and it is going to predict the maximum concentrations at the axis of the plume. However, these concentrations will be predicted above the ground. So when this contribution, which is equal to the concentration before here, so these concentrations are predicted above the ground by the imaginary stack. Therefore, these concentrations can be added to the actual concentrations to compensate for the concentrations predicted by the actual plume inside the earth. So for this case, when we see the concentrations of the actual plume inside the earth, so these will be compensated by the virtual stack source, and these concentration will appear above the ground. So this concentration will be added to the actual one, and therefore we have the plume concentration to be rather correctly computed at these locations. And likewise, we have to do this as the plume progress in x-axis with the along the x-axis in the downwind direction due to the wind speeds. I hope this will help you visualize the plume pattern, Gaussian plume pattern as it progress in the downwind direction.